Okay, so let's continue. So previously we have computed dy dx and d2y dx squared from the y equals to ax e negative 2 plus ix. So what we do here is we need to substitute everything into the original ODE. So yeah, let's continue there. So we put 3 minus 4i ax e negative 2 plus ix plus ix, okay, plus negative 4 plus 2i ae negative 2 plus ix and plus 4 times the dy dx, which is this whole thing up there. It's tedious and you're prone to make mistake. You're bound to make mistake, but just be careful. And plus 5y, 5 times ax e negative 2 plus ix, and this one equal to e to the power of 2x times cos x, but we don't want to put it in terms of cos x because we want to put everything in terms of Euler form. So it's negative 2x e ix, so e negative 2 plus ix. So this one equal to e negative 2 plus ix. Although we take note that cos x just refer to the real part of it. So yeah, you can compare the coefficient for this long equation here. So when you just compare and you collect all the terms together, yeah, let's do that quickly. Ax e negative 2 plus ix. Then when you collect all the coefficients together, you get 3 minus 4i minus 8 plus 4i plus 5. And this whole thing actually equal to 0. So you can eliminate this eventually. And plus with ae negative 2 plus ix. Then you collect the coefficient together, you get negative 4 plus 2i plus 4. Then this whole thing will be equal to e to the power of negative 2 plus I times x. And then you want to compare the coefficient. So 4 minus 4 is 0, so 2i a e negative 2 plus ix equals to e negative 2 plus ix. So you can compare to a equals to 1. So a equals to 1 over 2i. Okay. So then your yp, so oh, I have something here. So let me clear. So a equals to 1 over 2i. Then your yp is ax e negative 2 plus ix. So since a is 1 over 2i, so your yp is 1 over 2i x e negative 2 plus ix. Yeah. So we want to eliminate the I here because it's not nice to be working with some imaginary number. So what you can do is, if you want to delete the I down here, you need to multiply with I up here. But since this is not equal to 0, this is not no right hand side and left hand side. So when you multiply with I, you also want to divide with I as well. So then you the rest you just bring it down. Okay, so here you will get I over 2i squared times x times e times negative 2 plus ix. So you have negative I over 2 because I squared is negative 1 and x e. Now you can convert it back to the cos and sine notation. So you can break it down. So the negative 2, you just take negative 2 times x outside, and then e to the ix, this term you can convert it into cos and sine. So e to the ix is cos x plus I sine x. So here we can take this I to multiply inside. Okay, so what we have is then negative 1 over 2 x e negative 2x I cos x plus I squared sine x. And then you have negative 1 over 2 x e negative 2x I cos x, and I squared is equal to negative 1, so minus sine x. Okay, notice how things have changed here, because now this is your yp, but your yp actual is only the real part of your yp. So the real part of your yp is the one that do not involve this I term. So the real part of your yp is just 1 over 2, negative 1 over 2 x e negative 2x times negative sine x, and thus the negative term will eliminate itself, and you just end up with 1 over 2 x e negative 2x sine x. So this is your yp actual. Do not stop here. Your job is not done yet. So y total equal to yc plus yp actual 1. So yc was c1 times e negative 2 plus I x plus c2 times e negative 2 minus I x plus yp. So plus 1 over 2 x e negative 2x sine x. So this is your final solution for the given ODE using the first method, which is the Euler's notation. Okay, so second method is we're going to use the alternative method, which is we propose the yp in terms of c cos x and d sine x. Okay. Okay, so I'm going to go through this example, which you already have in the book or in the notes. Okay, so this is the second alternative method to use to solve the same example. Okay, right. So I'm just going to go through some of it, but it's really tedious, and I really advise you to just try to attempt it on your own also. Okay, so we don't have to repeat the YC, so we can just take the same YC. So your YC is C1 e times e to the power of this plus C2 e to the power of this. But it's more useful this time to put it in terms of cos and sine. So you put it e negative 2x and a cos x plus b sine x. Okay, so this is your YC. So just take it as it is for now. So now this time we want to work on the yp. So we propose the yp to be e to the power of negative 2x. This time, instead of taking the real or imaginary part of the cos x, so we put c cos x plus d sine x as the particular solution for the cos part of the right hand side function. And we can check whether yc and yp are linearly independent or not. So since this value here and this value here are the same, e to the minus 2x and e to the minus 2x. So yc and yp are linearly dependent. So we need to put something extra effort. So we propose another yp. So yp is, we put an x in front. So x e negative 2x, and the rest would be the same. Okay, and then now comes the hard part of finding the coefficient, because now you need to do the dy dx and d2y dx squared. So this one is really a pain in the, well, you can follow the steps here. So now I've shown you that we are already, okay, I've shown you that this is the yp that we're proposing, such that it is not linearly dependent with the yc. So when you differentiate dy dx, then, well, okay, oops. Okay, so differentiate, and then, well, you need to be careful in differentiating, because this is your u, this is your v, but inside your u, you got another two function that you need to differentiate. It's a product rule. So you need to do it one by one. And I'm sure you know how to differentiate already, and it's just a matter of being careful and collecting all the coefficients together, and just be careful lah. Okay, so this is your dy dx, okay, this whole thing here. And then you need to differentiate again with respect to x to get the second derivative, d2y dx squared. So make sure you just follow everything diligently such that you be careful. I think there's a typo in the coefficients collecting, but I've tried, but it's too much effort and it's, well, it's too tedious. So I guess you can do it on your own. I just show you how to do. Okay, so this is your d2y dx squared, and this is your dy dx. So, and then this is your original y. So what you do next is to substitute everything into the given ODE. Okay, so when you do that, and then you compare the coefficients and get the values of c and d. And when you get the values of c and d, then you can put in the original proposed YP. So notice that when you do this method, you don't have to worry about real and imaginary part of the YP. YP actual, either real or imaginary. You don't have to worry where the I is, because it will take care of itself. So as you can see here, if you do everything correctly, you will end up with the particular solution where c equals to 0, then the cost term here will become 0. Thus, you will end up with YP equals to this, which is the same answer like what we have in the using the first method just now, which is this is our YP. Yeah, you can see that it's the same. 1/2 x times e to the 2x times sine x. So it's the same here as well. So yeah, it's up to you. You explore on your own how to do it, because, well, mathematics really, like, it's not supposed to just be a lecture. When you want to learn it, you have to do it. You have to follow the exercise one by one, line by line, and be careful along the way. Okay, so that's all for the examples regarding the non-homogeneous second order linear ODE. So there are many examples in the notes, so you can follow through step by step. So try to do the rest of the examples, and let me know if you have any confusion issues. Okay. Right, so next is to take a break before we continue with the method of variation of parameters.